are continuing with stick force, and if you see, so far we have derived expression Fs equal to K half rho v square to A plus Ch delta t into delta t, so, and then minus K W by S Ch delta by Cm delta E, this is also Ch delta E, dCm by dCl free, right. Please understand one thing, whatever derivation you have done, you should do once, and you need to focus on something very important. After doing all those juggleries, we got stick force expression like this. So you focus here. Many times you might have seen I write Ch delta, or I may write Ch delta E. So these are similar things, same things. Actually, sometimes I forget to write delta E, or sometimes I may be writing deliberate delta. These are all, this is what is Ch delta E or Ch delta. This is the hinge, elevator hinge moment derivatives, right? You know that Ch alpha t, Ch delta or Ch delta E are same thing. Now come back to this expression. What does this expression tells you? It tells you the stick force applied, or while required to apply the stick force, will vary with dynamic pressure, and the first term will only be bothered about the speed. That is, the stick force will be dependent on the speed or dynamic pressure, and that contribution comes only from the first term. If you see, interestingly, the second term, it is independent of V, right? So stick force contribution towards changing with V comes from the first term. From the first term, and not from the stability characteristics. This is something surprising, right? So we need to again ask ourselves a question. Whenever we are talking about stick force, what we are doing actually? We should know this very clearly. I am applying the stick force to change the trim of the airplane from one equilibrium to another equilibrium, or one trim to another trim. That is, if I have Cm and Cl here, I was flying here, I want to go from one trim to another trim too. Okay? So for me, the force requirement, or the slope of force with speed, or the gradient with respect to speed, as far as force is concerned, I should be more bothered about the trim only. And common sense says, if airplane is highly stable, highly statically stable, then this gradient will be large, right? Because it will always resist, right? So now to get that understanding explicit, we will study the case at trim, right? Okay? That is why we will now go for dFs by dV. We'll try to find out at V trim. How does it function? How does it vary? Clear? If we take dFs by dV here, you will get only this term, with 2 will come here. For example, if I do it here, I'll get dFs by dV as K rho V into A plus Ch delta t into delta t. That's all. This term will not contribute. So what is that I'll get? Let me write clean. dFs by dV will be equal to K rho V A plus Ch delta t into delta t. Right? That's why I was telling this gradient doesn't bring the insight in terms of stability, which comes through dCm by dCl free. It doesn't come directly. You cannot see immediately, oh, something is happening here. So we'll do a trick. Since we know that all this dFs by dV, we are talking about a trim, so we'll analyze dFs by dV at V trim. Okay? Let us see what happens. So I write the statement like this. Suppose it is required that, let me write this, that the trim tab always be deflected to trim out the airplane, This is the language the pilot will be using. Remember, he is the most important person for us, right? And this is the language you see the pilot will say, I have trimmed out the airplane. It means it's a hands-off, Fs equal to 0. No stick force is required. You can fly like this. And this job is done by delta t all the time. Okay? And you know how it is done? The mechanism we have already discussed. Suppose the elevator has to be kept at this angle for trimming at a particular CL, and you are doing it by pulling the stick. We are trimming at a lower speed, so elevator has to go up. But then, as long as you hold the stick, okay, this gentleman will be like this. The moment you release the stick, because it's a reversible system, then elevator will also try to go back. So how to hold it without applying the stick force is put a trim at this tab, and this tab will generate a hinge moment, and which will ensure that this is kept at this position, right? So in a language you say, assume that delta t is rolled so that trim is achieved, okay? Correct? So that is what the language is, trim tab, so that Fs is 0, which is trim, or in pilot's language, it is trim out the airplane. I have trim out the airplane, okay? Now with this understanding, let us see how to formulate. So using this equation, we will try to find out what is Ch delta t into delta t to ensure that Fs equal to 0. So this is a statement that always be deflected to trim, right? So always delta t is deflected such that Fs is 0. I want to know what is this contribution. So from here, if I put Fs equal to 0, then I get k half rho v square into a plus Ch delta t into delta t minus k w by s Ch delta e by Cm delta e into dCm by dCl free. So if I do this, I get Ch delta t into delta t. You should do this simple derivation, will be 2w by s, okay, by rho v trim square, right? Now all is happening, this v is becoming, once Fs is 0, v is nothing but v trim. So this will be rho v trim square Ch delta by Cm or delta E, Cm delta E dCm by dCl free, right, minus A. A is here, okay, and you know the expression for A. So what is this? Let us have an interpretation. What is the interpretation of this? For a given stick-free stability, given hinge moment coefficient, given elevator control power, for a given wing loading, and at a V trim, I need to deflect delta t such that Ch delta t into delta t is equal to this. Then it will be trimmed. Fs will be 0. No stick force is required. Right? So we are flying using a trim tab. Okay. Now what I do, this Ch delta t into delta t, I substitute here. Correct? Then what I will get? If I substitute in this expression, then I will get Fs equal to, you please derive yourself, Fs will be equal to k w by s CH delta E by CM delta E into DCM by DCL free to V square by V trim square minus 1. You may get a confusion that we have put Fs equal to 0. From there you have got Ch delta T into delta T. So if I put it here, then it should become 0. No. If I put it here, this Fs will become 0 only when V equal to V trim. Is it clear? I repeat, you may get a confusion that Fs equal to 0 I have put here. From there I have got Ch delta T into delta T. Now this gentleman I am putting it here. So Fs should become equal to 0. Answer is no. This I have got at V trim, but I am talking about in general V. That is why once you substitute that, you get expression like this. Is it clear, everybody? Okay? Or should I do it? No. Okay, I will not do it. You can do yourself. Just put this expression here, and you will get this expression. And if you are finding it difficult, which you should not, write in the forum, will give the detailed derivations. But I'll be disappointed if you cannot do one or two such derivations, right? I'm sure you're smarter than me, you will be able to do it. So this is Fs. Now what is dFs by dV at V trim? That is our question we are looking for. So you could see first I find dFs by dV, so this will be K W by S CH delta E by CM delta E DCM by DCL free, and here I will get 2V by V trim square. I know that I am evaluating dFs by dV at V trim, so I will put here also V equal to V trim. So if I put here V equal to V trim, then V trim and V trim square, one V trim will be there, and you will get an expression dFs by dV at V trim equal to, which I am going to write now. So at V equal to V trim, you will get dFs by dV at V trim will be equal to K W by S CH delta E by CM delta E DCM by DCL free into 1 by V trim, or I put 2 here. This is the expression. So what is the physical interpretation of this? If I want to find out this gradient, then I know that for a lightly loaded airplane, that is whose wing loading is less, like gliders and all, dFs by dV also will go down. Okay? Also you know that it varies for other things given a constant, it varies inversely with V trim. If you are trying to trim at a lower speed, dFs by dV will be larger. Okay? Also you could see if you make, so let me write down this, dFs by dV at V trim, okay, will be proportional to W by S, very important parameter, wing loading. Also I see dFs by dV at V trim is proportional to, or inversely proportional to V trim. That is, if I am trying to trim at lower speed, dFs by dV will be more. It goes inversely. And also another thing which we are looking for, ds by dV at V trim is proportional to dCm by dCl free. So you could see that if I take CG forward, then dFs by dV, the slope will, gradient will increase. More stick free stable, more the dFs by dV. Okay? So these are the understanding from this expression. Now if I just plot it, the Fs required by the pilot. So if I see before I plot, K I know is negative, this is positive, this is negative, this is negative, so this becomes positive, this is negative, So total this dfs by dv at v trim sign is positive, but we have seen that we have taken push force as positive, but while plotting we are putting it here pull, which is negative, and push here positive. So you see this will be something like this, v trim. Yes, by dv, speed. And at trim, this is v trim. What does it say? If we want to increase v trim from here to here, you have to apply a push force. So consistent push force, I am increasing the v from v trim. V trim 1 to v trim 2, or v trim 2 is more than v trim 1. I am increasing the speed for trim. I am talking only about trim, not transients. Please understand. Similarly, if I try to trim the airplane at a speed lower than this v trim, let's say here, it says I have to pull it, which is also consistent. I want to reduce, pull. If I want to increase, push. Now what is happening here, if I come back here, if I am to increase the trim speed and to trim at a higher speed, remember these are all unaccelerated flight. This you should not forget. That is lift equal to weight. So what we are trying to do, and lift, you know what? Lift equal to half rho v square SCL, that is equal to weight. Now if you want to trim at a higher speed, you are pushing it. You are pushing here, that means you need a push force as per this diagram. And the push force will do what? As I push, elevator should go up or go down. Check from here. If I am increasing the speed to maintain the lift, to ensure it is equal to weight, CL has to go down. So if I push, the elevator should go down, so that angle of attack is reduced. If I want to pull, so elevator should go up. So these are all linked. Okay, that's why we say when I am pushing, elevator goes down. When I am pulling, elevator goes up. All these things get connected. One thing you understand: suppose you are at a V trim here, and you have applied a pull force. Now you have trimmed the airplane at this V trim, and now release the stick. Because it is a reversible, you will find it will try to come back to this trim. That is where your stability with respect to speed comes, and you could see that if the slope is very large, larger the slope, then external disturbance will not be able to alter the V trim. It will take larger dfs by dv, whether pull or push. Okay? But there is a limit how much gradient a pilot can handle. So that decides the handling qualities of an airplane. Okay? This part is extremely important, and you must understand this carefully. Okay? Thank you. Let us now think what we have done. We have calculated Fs, we have calculated dfs by dv at V trim. Right? Some time back, we also calculated what is the delta E required for particular CL trim, right? Okay. And from here, we realize one thing from this concept, that there is a CG location at which aircraft becomes statically neutrally stable. Okay? Neutrally stable. So from there we have defined neutral point. Then we have done maneuvering flight, and there we have defined NM, maneuvering point. These are all stick fixed, right? These are all stick fixed. That is, we have not allowed the elevator to float. Then we have also calculated what is delta E required for maneuver. From there only we got maneuvering point. We have also computed some expression like d delta E by dn, and we try to interpret this as elevator per g. Okay? Elevator angle per g requirement, right? Which comes, and that is exactly we used. We told that the CG location at which d delta by dn is only maneuvering point, stick fixed. if you see in similar way, we want to find out dfs by dn, this gradient. This is extremely important gradient. This is what pilot will be feeling, right? And also, we would like to know what about stick-free neutral point, which we have already derived expression to find out what is the stick-free neutral point. So our aim now will be to develop an expression for dfs by dn. We have already developed expression for d delta E by dn, through which we defined something called maneuvering point, and which is, what is the maneuvering point? It is the CG location at which d delta E by dn equal to 0. That is, beyond that you won't be able to really, you want to accelerate the airplane g, then it is going to have a structural failure. Okay. So what we have calculated there is maneuvering point using d delta E by dn expression. We put d delta E by dn equal to 0 and found out what is that xg location at which d delta E by dn was 0, and that is the maneuvering point. Similarly, we will now try to find out dfs by dn, and we will try to find out a stick-free maneuvering point. This is called a stick-free maneuvering point. Like this was called a stick-free neutral point. And what was this? A stick-fixed neutral point, and this is a stick-fixed maneuvering point. When you talk about stick-fixed, we are talking about delta E and N, delta E and CL. When you are talking about stick-free, we are talking about stick force N and stick force and CL. We will see how we build it up. Then also we will try to have a lecture on how to find various neutral points through flight test. Okay. So let us focus on dfs by dn. So the title will be stick force per g. For stick fixed case, it was elevator deflection per g. Okay. So now let us write first this big expression. Fs is minus g ac c half rho v square into neta t, and you are expert now, ch naught plus ch alpha t into alpha t plus ch delta E into delta E plus ch delta t into delta t. Right? This is a general expression where ch alpha t and ch delta E are the hinge moment coefficient, which are negative for most of the cases, because hinge line is ahead of the central pressure over the elevator, and ch delta t is also negative, and delta t is the tap deflection. Okay, this all we know by now. What is our aim? Our aim is stick force per g. That means we are talking about a maneuver. What sort of maneuver we have discussed? One was pull up, another was turn. Okay, and we know that if I see this diagram, if this airplane is going for a pitch up q or pitch rate q, which is q radians per second, and if this is the AC of the tail and this length is LT by convention, we all agree this is the tail momentum, horizontal tail momentum, then you know that because of this there will be a relative air velocity at AC, which is a resultant type. No? Let us say at AC we are taking this. This will be Q LT, and that angle of attack at tail additional because of Q. So as it is going down, the airplane is going down, this tail is going down. So this is the QLT, relative air velocity, and moving forward. So delta alpha t will be QLT by V, approximately. And then we need to understand one thing. That means the tail plane, because of a pitch rate maneuver, we will see additional angle QLT by V, which will give a nose down moment, right? And that is why you have to give a different elevator deflection. That you have done already in stick fixed case. But there is a difference, please understand. What I am trying to tell you is this: tail plane angle of attack is increased by this, only tail plane. We are not multiplying by 1.1 here. When we are doing correcting for delta E, there we have multiplied by 1.1. I will explain that as we progress. Okay. So what is happening now? Alpha t, I will write as alpha naught. Remember, this was CL by CL alpha wing to 1 minus d epsilon by d alpha minus IW plus IT. Right? This was for level acceleration, that is level flight. Okay. Now we are talking about maneuvering flight. So let me write here maneuvering flight. During maneuver, what do we know? L equal to NW. So CL equal to NW by half rho V square S. When it was level flight, that time we replaced CL by W by half rho V square S. But now it is a maneuvering flight. So load factor is more than 1. So I have to replace CL by NW by half rho V square S. So what this expression will turn out to be now? Alpha t equal to alpha naught plus NW by half rho V square S divided by CL alpha wing to 1 minus d epsilon by d alpha minus IW plus IT. If you listen to my explanation, you should be able to do all these steps at ease. Okay? What we are discussing here? We are discussing a maneuvering flight. We are trying to find out our model Fs for a maneuvering flight, and we have this expression. Okay? Here delta E is sitting here. What is delta E for a maneuvering flight? What is that maneuver I am talking about? We have already done for a pull-up. We know Q is nothing but G by V n minus 1. Okay? I will take the case of pull-up and I will write the general solution for turn, which you are supposed to do. Either you do it yourself or we will do through assignments. So we will consider pull-up case where Q is G by V n minus 1. What is the meaning of that? If I want to generate this much of load factor n at a speed V, then the Q, the pitch rate, should be given by this relationship. And then what we said, because of this Q, I have to be careful. I have to ensure that elevator is corrected. DCM by DCL fix, then minus 1.1 GLT by tau V square into n minus 1. We have already developed this in earlier lectures. You have seen this is the delta required for a pull-up maneuver. Okay? I was mentioning, please check here, when I am trying to see what is the alpha t seen here, I am very, very clear that when I am talking about alpha t, and this is alpha naught plus this, CL is NW this, but because of Q, there is an increment in alpha t, and that alpha t, Q, delta alpha t was Q, LT by V. No 1.1 factor is put here as far as tail angle of attack is concerned. This 1.1 came here because we are talking about the damping effect because of the portion ahead of the wing quarter chord, right? What actually happens, you see, as I am going like this, there is an increment in angle of attack here, so it gives stability. So as this portion goes up, this front portion, so there is a relative air like this. So they also try to discourage it, give nose down moment. So they also add to some sort of a stability, and we have to take care of that effect by elevator. That is why 10% increment was there to counter the fuselage effect, right, from delta E perspective. But as far as alpha tail is concerned, it is only increased by this much value, where Q has to be put equivalent to Q pull up or Q turn. We are considering a case Q pull up. So what is the understanding? This delta E, which is there with 10% increase because of fuselage effect, this delta E will come here. But when you come to alpha t, what should be the alpha t expression? Let us write it. This was alpha t for n equal to 1, it was like this. So for with load factor n, CL replaced by this minus IW plus IT, what will happen? What I have to add? I have to add this delta alpha, right? Because that is the amount by which tail angle of attack is changing. So I'll add this is as Q LT by V. So please be careful. We should be very, very clear what we are doing here. At this point, I need to know what is the delta E for a maneuver. We have already done. If it is doing a maneuver of load factor n, let's say for a pull-up case, delta required is this. We have already done in our earlier classes. Now, because of this Q, there is a change in the tail angle of attack by an amount this. So I have to put the value of Q also. So that alpha t, I will substitute here. So what I will do? Let me clarify. We are trying to find out what will be the alpha t. We know for n equal to 1, alpha t is given by this. We have already derived this. What is happening if the airplane is doing a pull-up with Q? And you know Q for pull-up is given by G by V n minus 1. So what will be the delta alpha here? Delta alpha tail will be Q LT by V, where from here to here this is LT, that is from AC of the tail to CG is LT. QLT by V is typically, already have done that. So now tail angle of attack has to be modified by this factor. So I'll add one is Q LT by V. This is coming from pull-up. What more? See, here it is CL. What will be CL now for maneuver? You know, L equal to NW. So CL will be equal to NW by half rho V square S. So these changes will come in alpha tail. Notice that we have not multiplied by 1.1. 1.1 multiplication was required for delta E expression because that some damping was coming from fuselage also. But here we are only solely talking about change in angle of attack at tail. Okay. If this is the expression for alpha t, delta E not already, delta E expression already have understood. Alpha t I have to put it here. Put this whole expression here, but remember what you have to do? I have to replace this Q by what? Q I have to write as G by V n minus 1. So what are the steps? You take this value of Q, put it here. L for L you put NW by half rho V square S. Take this whole alpha t, put it in this expression. So two things you have done. You have put elaborate expression for delta E, which takes care of the pull-up, and alpha t, which also takes care of pull-up. These two things we have to put in the Fs expression. Clear? So now once you put that, what happens? Once you put, you will get an expression like this. Fs equal to minus G neta t Ce Se half rho V square Ch naught plus Ch alpha t into alpha naught plus Ch delta t into It minus Ch alpha into Iw plus Ch delta E into delta E naught plus Ch delta t into delta t minus 2n W by S rho V square Cm delta into Ch delta dCm by dCl free plus 1.1 G LT by V square into n minus 1, in the bracket it is Ch alpha minus 1.1 Ch delta E by tau. This will be the expression. This is very mechanical. As I told you, if you put those expressions for delta E and alpha t here, then you can manage this. There's nothing to really get worried about it. So once we have this expression, now we do a trick. We are again trying to come back to a trim condition, which I call trim means when the Fs is 0. Now we want to use the definition of trim at n equal to 1, that is lift equal to weight. So what do? We say if trim tab is set for 0 stick force, that is Fs equal to 0, V trim at n equal to 1. Why this is important? How do I do pull up? I have a trim, lift equal to weight. Now I am doing a pull up. Okay? So I am assuming that when I have trimmed the airplane at level flight, the stick force is 0, and which corresponds to n equal to 1. From there I am going for n greater than 1 or n other than 1, and we are trying to find out what is the dFs by dn. It also says we want to find out dFs by dn about the trim, and trim for this case is lift equal to weight. Clear? Now, if you put this condition, if trim tab is set for 0 stick force, that is trim at n equal to 1, I repeat, because how you are doing the pull up, your trim is at lift equal to weight n equal to 1, right? And from there you are doing pull ups, and I am trying to find out dFs by dn, which is at the trim at n equal to 1. Trim means lift equal to weight. From there I am doing the pull up. So I am trying to find out dFs by dn about the trim when I am changing from the trim. Okay. So I can always write to find that condition Fs equal to 0, and that means n equal to 1, that is at trim. I will put 0 equal to minus g neta t c. Let me write this because it's very lengthy term. You don't get mixed up. Alpha naught plus Ch alpha into It minus Ch alpha into Iw. Ch alpha means alpha tail, that's alpha tail. Then plus Ch delta E into delta E naught plus Ch delta T into delta T minus 2 W by S rho V trim square. Okay, this is important. Cm delta dCm by dCl free plus GLT by V trim square n minus 1 into Ch alpha minus 1.1 Ch delta by tau. Bracket to be closed. Okay. Now see here. If I put n equal to 1, if I put n equal to 1, then you will see that this whole will correspond to a case where we had a level acceleration. Same term will come here, right? That shows that we are in right direction. That is stick force for level unaccelerated flight. When I put n equal to 1, those term goes to 0, and it will check that exactly that Fs expression will develop for level flight unaccelerated, which is cruise flight. You can check yourself. Okay, if I put this equal to 0, now what I have to do? From here, I can find out this plus this plus this plus this plus this, all of this, right? That will be equal to this term, right, divided by this term. Because as 0, so I take this term to a right hand side, okay, and I divide the right hand side term by this, then I will get this whole expression. And the whole expression in actual stick force expression will replace them by this expression. Okay, that is what I am trying to do. Please see, if this is equal to 0, then I can write Ch naught plus Ch alpha, alpha naught plus dot 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 Ch delta t into delta t. This term, whole this term, will be equal to 2 W by S by rho V trim square Cm delta, right? This whole divided by this term. Okay? Clear? So by doing this manipulation, let us see finally after doing all this thing, what do we get? There are too many expressions. Let us see what do we get and what sort of physics we are going to attribute to that. So we will get interesting expression Fs equal to minus G neta T AC C W by S Cm delta E CH delta E into dCm by dCl free into V square by V trim square minus N. Of course, it's not end of story. It's minus G NT AC C G LT rho by 2 N minus 1 into CH alpha minus 1.1 CH delta by tau. Huge expression you will get. Now what to do with this? So if I try to find out dFs by dN, I have to differentiate this. So I'll get an expression dFs by dN for a pull-up will be equal to G neta T AC C W by S CH delta E by Cm delta E into dCm by dCl free, then minus GNT ACC GLT rho by 2 to CH alpha minus 1.1 CH delta E by tau. This will be the expression for dFs by dN, and this is dCm by dCl free. What is our aim? Our aim is to find Nm prime. That is, what is that CG location? What is that CG location at which dFs by dN is 0? So I put 0 here, and I know dCm by dCl is xCg bar minus N naught prime. So dFs by dN, if I put it 0, this xCg becomes Nm prime. Is this clear? dFs by dN, now focus on this expression. Okay. dFs by dN is coming like this, where dCm by dCl free is here, and dCm by dCl free, you know, xCg minus N naught prime. And if I want to find stick free maneuvering point, which is Nm prime, what I have to do is put dFs by dN equal to 0, and whatever expression for xCg you get, that is nothing but Nm prime, because that is the CG location at which dFs by dN is 0. So if I put that 0, so I put dFs by dN equal to 0, and I get the expression for maneuvering point stick free as N naught prime plus Cm delta by W by S CH delta into rho by 2 GLT CH alpha minus 1.1 CH delta by tau. Let me erase this. Erase this part, now you are clear. Or in a neater form, if you want, this expression, you can further write in a neater form, this is equal to N naught prime plus Cm delta by W by S into CH delta rho by 2 G LT CH alpha minus 1.1 Ch delta by tau. Now, if I ask you a question, if this is a stick free neutral point, so Nm prime will be here or Nm prime will be here if I am measuring from this case. One obvious way of answering this question is, during maneuver the aircraft become more stable, so Nm prime should be somewhere here. It is more stable, so you can travel CG more. And now if you check from the expression, you see this is negative, this is negative, so negative is positive. क्या हो गया यार? Nm prime क्या है भाई expression? If I ask which way Nm prime would be with respect to N naught prime, you know it is a maneuvering stick free neutral point. So by our own understanding, it should be aft of N naught prime. If you see the expression, this is negative, and here between Ch alpha and this term, this will dominate, and there will be minus sign here. So overall this term will become greater than 0. So Nm will be more than N naught prime, and this will be somewhere here. Again, see this, by understanding, since it is maneuvering, so it will be more stable. So whatever stick free neutral point was here, because of maneuvering, the stick free maneuvering point will be aft of stick free neutral point, and that you could see from here. This is negative, this sign is negative, this become positive, and the sign is decided by this, sign of this and sign of this. Generally this factor is more than this factor, and the minus sign dominates here, so that makes it positive. So most cases if Nm prime will be aft of N naught prime. One advice to all of you, all this expression you go through once or get the final expression, understand what I am telling you. That's more than important, right? You should not get lost into big expression. These are simple expressions to derive, and you derive once, and then only remember the final thing. I would not expect any memory. I don't want you to remember this formula, all these big things. No question. As a flight mechanics man, these are available to you. You need to know physical interpretation for this so that you can utilize it for design purposes, right? I don't want to waste your time in memorizing all those big expressions. So feel relaxed. Only my request is, sit with the pen and pencil and derive this expression the way I have told you. Okay? Thank you very much. We will finally conclude this section by telling you how to calculate neutral point, maneuvering point using flight data or through flight test. Okay?